NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Hey, good evening, ladies and gentlemen. How's everyone tonight? Woohoo! Good, Michelle. All right, man. Well, thank you all for coming out on this lovely Valentine's Day. So we appreciate your attendance tonight, for sure. Concepts for directly and deliberately manipulating Earth's climate system, collectively referred to as geoengineering, have been proposed as contingency responses to global warming. Their consideration is motivated by accelerating fossil fuel use and growing evidence of rapid changes underway in our planet's atmosphere, land, and oceans. While stabilizing and reducing greenhouse gas emissions provides a direct long-term solution to mitigating climate change, establishing effective strategies and making substantive progress may take time. Some forms of geoengineering, in concert with mitigation efforts, have been suggested to avoid or reduce the risk of the most damaging climate impacts, such as abrupt and irreversible tipping point events. Yet geoengineering itself is complex and fraught with additional issues and risks that are still poorly understood. Satellite observation systems can play a key role in improving scientific understanding and risk assessments for geoengineering, including the risk of geoengineering research itself, in a rigorous, open, and transparent fashion. This talk will cover the motivations and risks of geoengineering and what can be done to support informed decision-making. Tonight's guest is the Chief Engineer for the Earth Science and Technology Directorate at NASA's Jet Propulsion Laboratory. He received a BS in Electrical Engineering from Auburn University and studied physics and astronomy, but not systems engineering, despite nearly 25 years practicing systems engineering on 7 missions. He was, in fact, the Chief Engineer for development of the Kepler mission that is currently searching for Earth-sized planets around other stars. He is the recipient of 2 NASA Exceptional Achievement Medals and the agency's Systems Engineering Excellence Award. In recent years, he has adapted and applied the discipline of systems engineering to informed responses to climate change. Among other tasks, he is a visiting researcher at UCLA's Joint Institute for Regional Earth System Science and Engineering, and is the U.S. coordinator for the Megacities Carbon Project, an international pilot activity to monitor the world's largest emitters of greenhouse gases. Ladies and gentlemen, please help me welcome tonight's guest, Mr. Riley Duran.
Thanks, Mark, and happy Valentine's Day. And I'd like to apologize in advance for any domestic discord that arises from your choice of entertainment options this evening. Let's see, before I get started, I want to thank the Keck Institute for Space Studies for supporting a study we did about 1.5 years ago on options for monitoring natural analogs to geoengineering. I'll talk about what I mean by that in a minute. I also want to thank my boss, Dr. Diane Evans, who's the Director of Earth Science and Technology at JPL, and my colleague, Dr. Mike Gunson, who runs the Global Change in Energy Office at JPL, for giving me the support to work in this area for the last 5 or 6 years. By this area, what I mean is in 2008, JPL founded the Global Change in Energy Office with the strict purpose of trying to extend and apply the lab's capabilities in remote sensing and Earth system science to societal needs, right? So moving the research to applied science. And as a result of that, a number of us have been focused on climate change mitigation, adaptation, and if you work in those fields long enough, eventually this topic comes up, geoengineering. So this is a recent development, and I'm going to try to explain some things tonight about what we're learning. Before I go on, I want to explain this cover photograph I picked. I picked it not just because it's pretty, but because it says several things or several themes that we're going to cover tonight. What you're looking at is an image taken from the International Space Station at night over North Africa. And what you see are night lights. This is the mouth of a Nile River, the mega city of Cairo, and these are lights of settlements, human settlements stretching down the Nile River. There's the Red Sea. You can see settlements along the Red Sea. You can see outlines of continents at night looking at night lights. And what this illustrates is the vantage point of space allows us to see the human footprint on planet Earth. We are capable, and have been for some time, of modifying the planet on a global scale. We are literally engineering the surface of the planet, and as we're going to see, we're engineering the atmosphere and the oceans. The second point is this image illustrates the critical dependence of human systems and society on natural resources, in this case, the Nile River. There's a reason why all the people in Egypt, or where the lights are clustered along the Nile. We depend on fresh water for food, for drinking water, for energy, for transportations. And it's not just Egypt that's dependent on the Nile. The 10 other countries that share this transborder resource depend on it. And this is common around the world. It's common in the Middle East, it's common in Asia, the Americas. Here in the U.S., in the western U.S., we're all familiar with how scarce water is. And it's going to become increasingly difficult and challenging to manage this resource because of two conflating issues. One is growth and consumptive use because of population pressure and development, and the other one is water availability because of the threat multiplier of climate change, right? Water is going to become the new oil in the world. It has national security implications, and it's something to watch. And the last thing I'll say about this figure is more subtle, but if you look at the edge of the Earth here, you'll notice this kind of almost ghostly outline above the limb. That's our atmosphere. And whenever I see images like this, I'm humbled and a little bit worried because it makes you realize just how thin this blanket of air is that separates life on Earth from the vacuum of space. And it's utterly dependent on relative concentrations of trace gases, of invisible gases you can't see, taste, or smell in the atmosphere. And we're going to talk about that. Okay, so tonight we're going to cover the following topics. What is geoengineering? What are the motivations for considering it? Why would we ever try this? How might it work, at least in theory? You're going to see that the devil's in the details. What do we need to know to inform decisions? And I mean, those of us who work for federal agencies, how do we inform decisions of policymakers and governments? But for all of us as citizens, how do we make personal decisions about the perceived risk and the real risk of geoengineering versus other actions? And does this suggest we need to find new ways to think about how we're operating planet Earth? Okay, this is a test for us. Two disclaimers before I go forward. One is, just because we're talking about the need to assess the risk of geoengineering doesn't mean we're advocating doing it. Don't get me wrong. I'm here to advocate for understanding the risk and the uncertainties, not to argue for a particular solution. And secondly, since as far as I'm aware, nobody at JPL or NASA has a position on geoengineering, everything I'm saying are my own opinions, not some agency position. Okay, so some history. Back in the 1950s, scientists were studying carbon dioxide, or CO2, in the atmosphere, and they were trying to answer the question, where does it go? Does it just evaporate? Does it go in the oceans? If so, how long does it take? And two scientists down at the Scripps Institution of Oceanography in La Jolla, Dr. Roger Revelle and Hans Suess, made a discovery. They realized that CO2 lasts longer than anyone had thought. And so they wrote this paper in 1957 where they said, human beings are now carrying out a large-scale geophysical experiment. And they were referring to the unprecedented growth of carbon dioxide in the atmosphere due to fossil fuel burning and its residence time in the atmosphere. And we'll get into that in more detail in just a second. A few years later, Dr. Revelle participated in a panel that President Lyndon Johnson convened on threats to the environment. And this is one of the first official references to geoengineering. They said a change in the radiation balance of the Earth and the opposite direction from the warming caused from greenhouse gases could be produced by raising the reflectivity or the albedo of the Earth, right? So this is the first kind of official reference to geoengineering. And over the decades that followed, some very outstanding scientists, both in the Soviet Union and the U.S., proposed in the scientific literature that we consider this as a fallback or emergency response, including Nobel laureate Paul Crutzen as recently as 2006. Now, scientific literature is great for being peer-reviewed, but if you want to get people's attention, you'd like to get your picture on the cover of Rolling Stone, or maybe have somebody do a caricature of polar bears frantically trying to geoengineer. But all joking aside, there's a very serious motivation for this, and the people who've been thinking about it, for the most part, are very careful and thoughtful. And let's talk about that. So let's look at that language, a large-scale geophysical experiment. What was Ravel referring to back in the 1950s? What he was talking about is this curve. It's called the Keeling curve. It's named after Charles Keeling, another researcher at Scripps, who began making very accurate and sustained measurements of CO2 in the atmosphere at the Scripps Pier back in the 1950s. And that's the result of this upward tick you see here in the red curve. This is carbon dioxide. These curves that go back in time about 2,000 years, they're extracted from gas samples that have been trapped in ice in Antarctica. And scientists can dig this stuff up and look at what the concentrations were going back in time. But this is called the hockey stick plot because for several thousand years, at least on this plot, it was flat and then suddenly it started to tick up. Well, this knee in the curve corresponds with the start of the Industrial Revolution, and it tracks perfectly the amount of fossil fuel we've burned and the rate that it's going up. Okay, these correlate really well. So what does this say? Well, it says that it's unprecedented. You actually have to go back in time well beyond the origin of this chart to about 300,000 years before you get to 300 parts per million. Today we're closer to 400. But to get to just the 300 parts per million, you have to go back to before Homo sapiens appeared on the planet Earth. Keep in mind that we've only had agriculture for a few thousand years. This is before our species walked the Earth. And if you want to go back to levels approaching where we are today, you have to go back about 15 million years in the record, when the Earth was a fundamentally different place, right? So this is new for us. In fact, it's so new that some scientists are beginning to say we should change the name of the geological era that we're in to the Anthropocene, meaning that we are now, humanity is a geological force. We're actually changing the chemistry and the structure of the planet on a global scale. Okay, so how did this happen? This is a plot generated by scientists at the Oak Ridge National Laboratory going back to the 1800s, reconstructing the rise of fossil fuel emissions along in the world. So what this is showing you is the growth of cities and industrialization in the U.S. It started around 1890, and it peaked, or it settled in around 1960. So by 1960, the U.S. infrastructure that we know it was largely locked in. We've had growth since then, but by and large, the U.S. that you would recognize today was in place by 1960. It took about 70 years. Now, if we shift focus and rock back in time and look at Asia now, and we're going to look at Japan, the same thing happened, although they got a later start. So starting around 1910, you see the rise of Japan. You'll see fossil fuel use starting to peak up in Japan in 1910, and by 1980, the same thing had happened. They had locked into their current infrastructure, and most of their growth occurred. So again, like the U.S., about 70 years. And if we rock over and look at China now, the same thing began there much later, in 1960. So China, and now you can see India, are starting to grow out their infrastructure and their dependence on energy. Now, this plot only goes to 2001. So we don't know when China's going to top out, but if they follow the pattern of other developing countries like the US and Japan, and it takes 70 years, they won't peak out until about 2030. And by the way, this corresponds pretty well with what economists say. If you watch what's happening with China's economy, despite the economic turndown, they're growing really rapidly, like 10% a year annual growth in the gross domestic product. And India is not far behind. So this is what we call the carbonization of the world. And if that isn't drive it home for you, consider this picture taken of Shanghai in 1990 and then 20 years later. Same angle. This looks shocking, but this is exactly what happened in the U.S. at the turn of a century, last century, and in other places. It's not a new phenomenon. Okay, so what does this mean in terms of the Earth? Well, two budgets to know about. One is the carbon budget and the energy budget. Let's talk about the carbon budget. There are three places on Earth where carbon are stored. One is in the atmosphere. The other one is in the land in the form of vegetation like trees and soils. And the other place is in the ocean. And carbon cycle scientists call these reservoirs or pools of carbon. And the exchange between the atmosphere and the land and the atmosphere and the ocean are called fluxes. So these purple lines indicate the direction and the size of the fluxes. And what you should take away from this busy chart is they more or less balance in the case of the air and the oceans and the air and the land. This is the natural carbon cycle, and that's the way it was for most of history until about the Industrial Revolution. What happened in the Industrial Revolution is we began clearing land in large quantities. So this here is called the land disturbance due to chopping down trees and burning them and releasing the carbon that's stored in vegetation. And so today we release about 1.5 billion tons a year, or 1.5 gigatons, of carbon into the atmosphere globally from deforestation and forest clearing. The rest of the emissions from human activity come from fossil fuels. So again, during the Industrial Revolution, we began digging up fossil fuels and burning them and releasing the carbon that was stored underground for millions of years. And today we produce about 8.5 billion or 8.5 gigatons. Actually, last year it was more like 9. So total human activity today produces about 10 gigatons or 10 billion tons of carbon a year that go into the atmosphere. And that's growing at about 3% a year. When Roger Revelle wrote his paper back in 1957, it was growing at about 0.7% a year. So it's accelerating. The other thing to take away from this image is, okay, what does this mean? Well, the carbon in the form of CO2, carbon dioxide, is a fraction of the atmosphere above us, and that causes the greenhouse effect, which we'll talk about in a second, but it also affects the ocean chemistry. So something to keep in mind, when scientists talk about climate change, we don't just mean global warming. We also mean that we're changing the chemistry of the oceans. And that's because it's very simple, all right, high school chemistry. If you take water and CO2, you get carbonic acid. Now, the ocean is naturally predisposed to buffer itself, just like the buffer solution you might use in your swimming pool. But over time, the pH is dropping. We can measure this. And what it means is the carbonate ions that are available to the marine ecosystems, including coral reefs and the plankton that form the basis of the marine food pyramid, are having a hard time building their skeletons. And one of the concerns we have is that those life forms will have a hard time existing if this chemical change continues. So just keep that in mind. It's not just in the atmosphere, it's chemistry of the ocean. Okay, greenhouse effect. This is a cartoon showing basically the Earth's energy budget. It's very simple to understand. The amount of energy that comes into the Earth from the sun, the visible light, scientists call it shortwave radiation, has to be balanced by the outgoing radiation from the heat. What happens is sunlight comes in. On average, about a third of it is reflected back into space because of clouds, which are shiny, and because of different surfaces on the Earth that are shiny, like snow and ice. The rest of it is absorbed by the surface of the Earth, and it's radiated back as heat, right? This is exactly what happens in your car, right? When you have the windows, sunlight, your windows and the glass are transparent to sunlight, but they are what? They're opaque to infrared radiation. So when your car heats up because light's coming in, but the heat can't get out when you've got the windows up. And that's what happens with greenhouse gases. A certain fraction of the heat is trapped in this blanket caused by water vapor, carbon dioxide, methane, and other greenhouse gases. Now, another thing you should know, there's a few complications in this story. This goes back to what Roger Revelle and others discovered. CO2 in the atmosphere lasts virtually forever. Let me give you a story on this. You remember a few years ago there was the Fukushima nuclear reactor meltdown in Japan, and there was a lot of concern here in Los Angeles and the West Coast about fallout, from radioactive isotopes that would come over the Pacific and make people sick. One of the isotopes that's common that people carry about is cesium-137. It turns out that cesium-137 has a shorter lifetime in the atmosphere than CO2, and the reason is the long-term uptake of CO2 has to do with ocean processes. It takes thousands of years for the CO2 that we emit today to be pulled out of the atmosphere. Another way to think about it is a bathtub. If CO2 is the water and you've got a bathtub, the bathtub in this case has no drain, or the drain's plugged. Just because we stop emitting CO2, if we were to stop tomorrow, the CO2 is going to be around for hundreds or not thousands of years. In fact, what we see is that about 50% is around after 200 years. So in human timescales, that's virtually irreversible. Another complication about climate change, and by the way, the reason I'm telling you this is as an engineer, I think about margins and robust systems and about being able to turn things around, right? What I'm trying to tell you is there are aspects of the climate system that are not robust. They have no margin, or they take us in directions in one direction and I can't go back. And we don't design airplanes and bridges and buildings and energy systems like that for a reason. They're hazardous. I'm trying to explain some of the features that are not robust. So one of the features is inertia, okay? Inertia, as a topic in physics, refers to a tendency of an object to resist changes in motion. So just like us on a Saturday don't want to get off the couch, an object at rest wants to stay at rest. An object that's moving wants to stay in motion. This is why you have to apply brakes to stop your car, or you have to wait a long time for it to slow down by friction. The same thing is true with energy systems, with economic systems, and with the climate system. What this means is that things that are already moving will keep moving. So I mentioned that China's undergoing rapid development. It would take a lot to stop that, all right, or decarbonize it. And the same thing, countries in the developed world which have high carbon intensities, we have a high standard of living, a high energy footprint, would take a lot for us to move off that. So what does this mean? Well, in 2009, all the nations in the world got together and they wrote this thing called the Copenhagen Accord. They didn't agree to cut emissions, but they agreed what's a target for avoiding quote-unquote dangerous climate change. And the target they agreed to was a global temperature rise should be no more than 2 degrees Celsius. There's a lot of information behind they picked that number, but just stick with it for a minute. Why? How are we doing against that target? This is a plot of projections of warming going out to about 2100, and there are many scenarios that you could look at, but these are just two. This is what I call the optimistic case, and this is the, well, it used to be the pessimistic case, now it's more the realistic case. What these curves refer to is they're called representative concentration pathways. Different groups, these are independent groups, were given basically criteria, and they said, make your own projection of what will happen with economic conditions or with future emission agreements, and then model it with the best models that we have of the Earth system, and predict how much warming we'll have by the end of a century. So the scenario that keeps us under 2 degrees C, right, is this one called RCP3, right? The so-called worst-case scenario assumes that we don't get a grip on the emissions and we end up going to about 4 degrees C temperature rise by the end of a decade, by the end of a century. And the concerning thing here is these little black dots and red dots are actually what we're doing. This is the emissions we're on. So we're deviating from the curve we need to be on. We're on this red curve. And in fact, the International Energy Agency has said that if we don't shift by about 2017, we're going to be locked in for a few decades. This has to do with inertia of energy systems and economic systems, right? What I'm talking about is an energy system that consists of 60,000 power plants around the world, and cars and trains and ships and so forth. So shifting this requires shifting the entire global energy system. So what does that mean? It means that if we're going to do it, we have to do short-term, we have to reverse our current emission trajectory so that we stop growing by 2020. We start doing significant reductions out here in the 2020s, and by the time we get out to 2080, we're in net negative emissions. That actually means that we have to start drawing down CO2 in the atmosphere. And now we're in the realm of geoengineering, and I'll talk about that more in a minute. So if we end up on this worst case curve, what does that mean? I'm going to pick the low end of this. I'm going to pick the optimistic number, 4 degrees C. Well, because the Earth doesn't warm evenly because of different feedback processes in the Arctic, a 4 degrees C, which is 9 degrees Fahrenheit warming everywhere on the planet, the average temperature, translates to about 11 degrees C or 20 degree Fahrenheit warming in the Arctic. If this comes to pass, there will be no more Arctic. We won't have ice in the Arctic. So this brings us to tipping points. This is another complication. What is a tipping point? This is a scientific description of it, but basically in words, what it means is that if you slowly change a system, think about like two valleys and you're slowly flattening them out, and there's a ball sitting at the bottom of this valley, and you slowly push the bottom of the valley up, ultimately, it'll get to a tipping point. And maybe a better way to describe this is if I'm standing back from the edge of a stage and you want to come up here and push me off, it's going to take more energy than if I'm standing right up against the edge. If I'm up on the edge just kind of balancing, you could knock me over with a feather. And once I start to fall, I'm going to have a hard time stopping. And if this stage is high enough, I may never get back up, or it may take me a long time to get back up. That's what we mean by tipping points. It means that it becomes very easy to tip over into a qualitatively different state. And once you're in the new state, you may not be able to get back, or at least not on time scales that you or I think about. It may take thousands of years, not a few years. Right. So what does this mean in terms of what the Earth does? Well, climate scientists have studied the potential for tipping points in the climate system, and there's a number of areas around the world where they've acknowledged that there are aspects of the climate system that could start a tipping point this century. That doesn't mean it'll finish. Some of these things, like in the Antarctic, could take hundreds of years, right? It may be irreversible, but we're not going to see the big impacts for a while. But some of them could happen very quickly, and I'm going to talk about a couple of them. Just to point out, well, what does this mean for you and me? Well, some of these systems have to do with monsoons in India, the monsoon in West Africa, or we're familiar with this in Southern California, the El Nino Southern Oscillation. These are features of the climate system that operate a certain way today. And the point is that they qualitatively change, utterly different than what we have today. It will change precipitation patterns and weather significantly. You're familiar with this if you follow the news. When we have La Nina, El Nino cycles, which are normal, those cycles will change. The other aspect, which is a little more concerning, has to do with climate feedbacks because of what happens in the Arctic. And let me talk about those two examples. So here's one example of a tipping point. This is Arctic sea ice. So what we're doing is looking at animation, looking down at the top of the world. And this is an animation based on 3 decades of satellite data. So this is NASA data, NOAA data, other data sets. And what you're seeing is an animation. This is accelerated. So over 3 decades, you're seeing the evolution of ice over a year. So remember, in the winter, it freezes back up. In the summer, it melts away. And the colors here indicate the age of the ice. So white means that the ice is about 10 years old or older, which means it's thicker. And the dark blue means the ice is only about a year old. That means it doesn't last year-round. It basically melts away. And what you'll see here as we get towards the end of the last decade, a lot of the ice starts to disappear. What's happening is it's not just melting away. It's this chunks of ice are slipping out through the Fram Strait here. And so you're seeing a smaller and smaller extent every year. But more importantly, you're seeing the ice get younger and younger, which means it's thinner. Another way to look at this is a paper that was just published a couple of days ago with one of our colleagues at JPL, was using satellite data again to look at over the last 10 years, and they're measuring the volume. And what they see here is in the autumn ice thickness, they see about a 30% reduction in the thickness or in volume over the last decade, 30%. So why is this concerning? It's what scientists call a positive feedback loop. What that means is, think of it this way, less ice. Ice is shiny, it's reflective. Less ice means you have a darker surface. Seawater is darker than ice. So that means more warming because dark surfaces absorb heat, which means less ice, which means more warming, so you can get a runaway. That's what we mean by positive feedback. It's not stable. And so what does that mean for the future? Well, this is a very busy chart, but these are outputs from about 25 different climate models, and there's a lot of noise in here. But what you should notice is there's a common trend that runs through most of these. So all these different colors are different climate models. But the red line is not. The red line are actual observations. These are measurements. And what worries people is that the trend over the last 10 years or so with the satellite observations is much steeper than the trend in any of the models. So what it says is change in the Arctic is actually outrunning the models. So it casts down on our ability to predict it. And it's not heading in the opposite direction. It's happening faster than we predicted. So that makes us worry that maybe we've already crossed a tipping point or we're close to one when it comes to sea ice. Another example, Arctic permafrost. So what is permafrost? Well, about 25% of the northern hemisphere is permanently frozen. It means it lasts for at least a couple of years as a scientific definition. Well, what is permafrost? Well, if you imagine that places like northern Alaska and Siberia are frozen all the time, then you have the potential for carbon cycles. You have frozen organic matter below the surface of the Earth. Maybe it was an old swamp or an old forest that's been buried and it's frozen and it never thaws. It hasn't thawed in thousands of years. Well, the best estimates today are we have about 1,900 gigatons or 1.9 trillion tons of carbon stored in the permafrost if you add it all up. That's about twice the amount of carbon that's currently in the atmosphere. If it was released at once, our goose would be cooked, literally. Now, most scientists will say that's a very low likelihood thing. We actually think that a much smaller amount may be vulnerable. But the question is how much, right? That's very active research. One of our good friends and colleagues at JPL, Chip Miller, is actually the lead scientist on an aircraft mission that's flying around Alaska trying to answer this question. How much of this is vulnerable? Is it the first few meters? How fast will it be released? When it does, will it act like a tipping point? Will it just kind of tick off and keep going? And how much of it is released as carbon dioxide versus methane? That's important because methane, I haven't talked about it yet, but methane is another greenhouse gas. And the point is that methane is much more efficient at trapping heat than CO2. On a 100-year time horizon, methane is 25 times more effective than CO2. And on a 20-year time horizon, it's 77 times more effective. And the difference between this all being released as methane or CO2 has to do with how wet things are or how much oxygen there is in the soil, because it has to do with microbes. Lots of big questions about what's going to happen. Again, positive feedback. Permafrost means more carbon's emitted, which makes it warmer, which means less permafrost. This is not a stable system. And in this case, what we mean by tipping point is you would expect if we didn't have permafrost, you would expect that as the Arctic warmed up and we had more warmer conditions and more plants soak up CO2, you would expect that the Arctic would be a net sink. It would draw down CO2 as the Arctic warmed. But if you're releasing more carbon and you've got this feedback loop going, you're now going to become a net source, right? So the question is, where does that happen? Where does that transition happen? Does it happen next decade? Does it happen 2050? Does it happen 2100? Best estimates right now are closer. And again, the concern how big that effect is depends on answering these questions. This is active research that's happening right now. We just finished the first season of these flights. Okay, so enough doom. What can be done? This is an elegant figure, I think, that Dr. Lynn Russell from Scripps put together. I like it because what she's done is she's illustrated, this is, by the way, this is the only equation we're going to talk about tonight, but it's the most important one when it comes to managing the Earth's climate. Well, what she's showing here, note these dates. These are dates that these physical laws were discovered and proven. These dates are the 1800s. This is 19th century physics, right? This has been proven again and again. All of our technology is based on these physical laws. For example, the first law of thermodynamics. The light coming into the Earth in the amount of sunlight has to be balanced by the heat coming out, right? That's this balance of the equation. On the left-hand side, you have sunlight coming in. That's represented by S. And how much reaches the surface of the Earth is reduced by the shininess or the reflectiveness of the Earth, the albedo alpha. The Earth responds to that sunlight by radiating heat, and that's governed by the Stefan-Boltzmann law. It's a very fundamental law. Minus how much is trapped by greenhouse gases, F. Okay, so if I use 8th grade algebra to rearrange this equation, what I find is that the Earth's surface temperature is proportional to the sunlight coming in minus the effect of albedo plus the greenhouse gas forcing. This is a constant. And for the timescales we're talking about, the sun is constant. So the only two knobs you can turn are albedo and the greenhouse gas. Okay, so now we're engineers. How do we save the planet? Okay, plan A that the human species is working on right now is to do two things, to mitigate and adapt. Mitigate means stop putting so much greenhouse gases into the air. This is stabilizing or slowing down the rate of emissions into the atmosphere. So this is what you hear about mostly in the news. It's about renewable energy, conservation, maybe putting a price on carbon, solar energy, trying to slow down the rate of emissions. The other one is to adapt. Notice that the arrow goes in the opposite direction. We don't control temperature, we respond to it. So the other thing that we're doing is we're preparing for the future. People are moving away from the coast. We're building seawalls. We're preparing for storm surge. We're trying to build more resilient energy systems. We're trying to deal with resiliency in agricultural systems. A lot of funding is being spent around the world on adapting, preparing for the worst. Okay, so that's plan A. Now, what happens if that's not enough? Here's where geoengineering comes in. Plan B has two parts. The first part is to literally pull carbon dioxide out of the atmosphere. It's not controlling the rate that we're emitting. It's taking what's there today and pulling it out. This is trying to address that CO2 is forever problem, right? So think about having a giant vacuum cleaner that's sucking CO2 out of the atmosphere. It's called carbon dioxide removal. The other scheme is to increase the albedo, right? So I can turn up the albedo, make the Earth shinier. And this is called solar radiation management. So remember those two terms. Okay. So there have been a number of schemes proposed for geoengineering, and I'm not going to go through all of them. I'm going to pick a few examples, but they're generally bent into two groups. One is solar radiation management, which is basically cutting back on the amount of incoming solar radiation, whether I'm using sunshades in space or doing things in the atmosphere or changing the Earth's surface. And the other option is pulling CO2 out of the atmosphere, CO2 removal, using a lot of different techniques. I'm going to talk about a few. So, method one for reducing the amount of sunlight hitting the Earth is called stratospheric aerosol injection. What does that mean? Well, scientists pay attention to what happens in the natural environment. And something they've known for a long time is when you have very large volcanoes, we see a drop in temperature around the world. Why does that happen? Well, very big volcanoes like Mount Pinatubo that erupted in the Philippines several times, but in 1991, it lofted so much stuff into the stratosphere in the form of aerosols, sulfur dioxide, that you actually get a haze. This dark layer here is an after photo. Here's a before photo looking at the atmosphere. Here's an after. And you can see this drop. You see this big uptick in optical depth. That's where we actually introduce some dimming of the sun. And it lasted for a while, right? This stuff stays up there for a while, a few years. And there's a measurable drop in temperature. And we see this repeatedly when large volcanoes erupt. We see it with Pinatubo. We see it with El Chichon. You can look back through the record and see evidence of changes. So we're taking a lesson from Mother Nature. So the idea is, well, if Mother Nature can do that, why don't we? So there have been a variety of schemes proposed, ranging from zany to pretty low tech. And they all have to do with getting aerosols into the stratosphere and keeping them there for years and years and years. So for example, if we used existing technology, if we used aircraft, this would be the equivalent of taking a small airline and just saying, you do nothing but spray aerosols in the stratosphere for the next N decades. So think about how much that costs. Buy your own airline and do nothing but spray this stuff into the stratosphere. I'll come back to why these things are problematic. I'm just giving you an introduction now. The other option for cutting down on the sunlight hitting the Earth is to focus on the low clouds. Okay, so you're familiar with this. If you've seen the marine layer come rolling in at night in the LA basin, if you've seen low stratus clouds, that's what we're going after here. Another lesson from nature. This is a satellite image with ship tracks. These little tendrils are literally the response of low clouds to ships steaming along. Ships spew out gunk from their smokestacks. These aerosols end up in the clouds. They aggregate, and they cause more water droplets sometimes. And when that happens, the clouds get brighter. So that's what you're seeing. You're seeing an enhancement in the reflectivity, or the albedo of these clouds where there was a ship. So geoengineers go, aha, I'll just build a giant fleet of robotic, solar, or wind-powered ships that'll just tool around the oceans, and they won't even use sulfur, right? They'll just they'll take salt water and they'll spray salt into the atmosphere, and that will work most of the time. We'll come back to why this has problems. While we're at it, why don't we just paint the surface of the Earth, right? You paint your roof white, you'll cool off. This is, I think, is kind of fascinating. This is a satellite image that some colleagues of ours used. It's a multispectral satellite image, and let me explain what you're looking at. You're looking down at the border of Norway and Finland, right? And this is a little misleading. In this case, the bright image means there's more vegetation, and the dark image means you're looking at just flat tundra. This is taken kind of during the summer. But what's important is to go, well, why is it different? I mean, these guys have the same temperature, the same climate. The difference is Finland has more reindeer. They have more widespread grazing, and so they keep all this stuff mowed down, right? So Finland has less plants along this border. Well, what does that mean? Well, because bare earth and vegetation is darker than snow, when spring rolls around, the snow melts earlier and quicker in Norway than it does in Finland. Finland gets about 2 more months a year of snow in this region than just on the other side of the fence, just on the side of the border. And that's a significant amount of energy. Right? So the geoengineers say, well, I got this big range in the north, and what if I could just do more? And which gets away from engineering. Maybe what we don't need is engineering, but reindeer engineering. We have genetic engineering. We'll just breed giant reindeer until they go wild and devour everyone. Okay, so shifting gears, let's talk about carbon dioxide removal. So how do we get CO2 out of the atmosphere other than using plants, which is one of the schemes? This is perhaps the quote-unquote safest method because it has an on-off switch, right? The way I like to describe this is a reverse power plant, right? If I have a coal-fired power plant, what does it do? It burns coal, it puts a lot of CO2 in the atmosphere, and we get energy out. This is the opposite. You put energy into the power plant, and it tries to suck CO2 out of the air. You don't have to be an engineer to realize how inefficient this is, right? It's far more efficient not to put the CO2 in the first place, i.e. less costly. But how does this work? It's very elegant, actually, it's very brute force. What you do is you have fans that pull air, ambient air, across something called a contactor. It's just a chemical sorbent, like sodium hydroxide. This is how CO2 scrubbers work, right? You then take that solution, that carbonate solution, and you operate on it, that is, put energy into it. You can extract CO2, compress it, and then store it underground in liquid form. This is the same technology that's used in so-called clean coal power plants. We call it conventional carbon sequestration, where you capture it at the point of burning and you sequester it underground. Now that storage has its own issues, but the geoengineering part here is the air contactor, the pulling it out of the air. So the idea is you build a bunch of these. Each one of these things is about 1 kilometer on a side. They're big. Think about building a great big power plant. But to make a big difference, you've got to build a lot of them. If you were to offset our current emissions, which again is growing, you'd have to build 30,000 of these things around the world, right? And that's about half the number of the power plants that exist today. And remember how long it took us to build all those power plants. So this may be part of the solution someday, but it won't happen overnight. And it has significant economic barriers. Okay, another carbon capture method is called ocean iron fertilization. The idea here is that you seed the ocean with iron filings and other nutrients. So you go out in the ocean, you dump iron filings in the ocean. This stimulates plankton blooms. Plankton are essentially little algae or plants which suck up CO2. And the idea is that they'll suck up the CO2, they'll drop to the bottom of the ocean, and done. Except we don't know how long it lasts. We have no idea what this does to marine ecosystems and the ripple effects, which is a general theme of geoengineering. But I include these two photos because this was actually done. This has actually been done a couple of times. It was most recently done off the coast of British Columbia back this fall by a private entity with no government review, no public review. It was basically a rogue effort. And this points out one of the concerns about geoengineering. Because the technology seems easy and cheap, I mean, how hard is it to dump iron filings in the ocean? Anybody can do it, right? So I'll come back to this big problem with geoengineering in general. So much for good intentions. Will Rogers got it right. If stupidity got us into this mess, why can't it get us out? Man was way ahead of his time. We can all think of examples where we've made decisions as a species that sounded like a good idea at the time and they didn't pan out. One of the most notorious for me personally is the story of the mongoose in Hawaii. So I'm a wildlife photographer in my spare time. I spend a lot of time tramping around in cloud forest around the world, and Hawaii is no exception. Well, in the 1800s, with the influx of population in Hawaii, they were being overrun by rats that were sneaking aboard the ship. So somebody said, let's get mongooses. Mongooses will eat the rats, and it'll take care of our problem. Except mongooses are diurnal, and rats are nocturnal. So they ignore each other. They never see each other. So what do? They gang up, and they kill all the native birds, which is really harsh. If you've never seen these birds, they're endemic to Hawaii. They are fascinating in terms of their evolution and their beauty. And I'm sure we can all think of examples where we've made decisions, especially with biological systems, that just didn't pan out. So, what could possibly go wrong with geoengineering? So let me give another example. I didn't show this option because I think it's so spectacularly bad. But it's best described by Futurama and Al Gore.
First up is Professor Ogden Wernstrom.
Wernstrom! Ahem! Ladies and gentlemen, I have placed in orbit a giant mirror that will reflect 40% of the sun's rays, thus cooling Earth. Observe. Problem solved.
Oh, that's a little bright.
You get the idea. It's JPL. You'd think we would be all over this, but we took one look at it and just no. So that's what can go wrong. So thinking critically, seriously, what are the problems with these? So this is built on some work by Alan Robach, one of my colleagues, and also Mike McCracken, and I've tried to condense it to look at both the solar radiation management and carbon dioxide removal. And if we just look at the climate system, environmental systems, there are a lot of issues. One is it's known from looking at volcanic eruptions and this cooling effect that you get uneven heating, and you actually cause drought in some areas. So country A decides to do geoengineering, and they cause a drought in country B. The missiles start flying. What happens if we stop it abruptly? If we can't get control of CO2 and we start injecting stuff in the stratosphere, it's costing us $10 billion a year, and we have an economic meltdown or a natural disaster or a volcano erupts and we can't fly airplanes for a while. What happens if that shield is removed quickly? We rapidly jump up in temperature. And the concern, even greater than that, is the fact of what we call instability in the system. If you whack a bell, it rings for a while. The concern of the climate system ringing like a bell and being unstable is a big concern. Climate models show this sort of stuff happens if you shut it off quickly. And there are a lot of other issues. We don't know what happens to ozone in some of these cases. We don't know what happens to cirrus clouds. If you make more cirrus clouds, you make things warmer. There are a lot of ripple effects we don't understand. And even more disturbing are the human system impacts, right? What happens if we're like Dr. Hornblatt in the space mirror? We screw up. What about the moral hazard? This is a big one, right? If humanity knew that scientists had a silver bullet that was waiting in the wings, that we could pull a trigger and save us, and we're going to wait and see how bad it is, would we keep cutting back on fossil fuels, or would we just go our merry way? This is a real concern in policy circles. Politicians are very worried about this. In other words, it's a slippery slope. And there are other issues. What about weaponization? If you grew up watching The $6 Million Man and The Bionic Woman like me, and remember there's an episode where the bad guy builds a weather machine and he's holding all the governments hostage. Well, this is not science fiction anymore. It really could work. Not to mention the distraction of spending cost and and again, arguments over the thermostat. Whose hand's on the thermostat, right? Look how hard it is to get international agreements on anything. So these are fraught issues. There have been studies, what I kind of call one-off studies. There was one that was done by the United Kingdom, the Royal Society a few years ago, where they tried to assess the relative affordability of some of these options versus the effectiveness. So ones up here in the right-hand quadrant would be considered optimal, but that raises a concern, right? If it's perceived to be cheap and effective, then in the words of Dr. Strangelove, it merely requires the will of trying this, right? And the perception of this could lead to unilateral action. And don't take my word for it. Listen to the World Economic Forum. Every year they put out a risk assessment. Just a couple of weeks ago they put out a risk assessment, and they listed 5 wild cards or X factors for the 21st century. Rogue geoengineering was one of those. This is The Economist and the business leaders worrying about somebody taking rogue action and just messing it up for everybody. So what's being done right now? Well, there are some national geoengineering programs. The United Kingdom has one. China has one. The Gates Foundation is funding some research, a small team in the U.S., and there are people actually planning field experiments next year. There are modeling efforts, which are pretty benign. They're fairly small scale. And very recently, the National Science Foundation in the U.S. funded a group, a team of research scientists led by Penn State, to look at climate responses across the board. Not just geoengineering, but they included geoengineering in the mix. As far as I know, the first such U.S.-funded research activity. So that's fairly new. If you were to do this, if you were to go about this systematically, what do you need to do to address those questions about geoengineering? Well, you have to address the governance, ethical, economic, and legal implications. You could take a gaggle of legal experts, social scientists, economists, and put them aside for years, and they would have to sort this out. There's a lot we can learn by studying volcanoes and ship tracks, do what we were talking about with the KISS study, the Keck Institute study. Models are the safest way to do this because you don't actually go out and play with the planet. This is important. This is what we do with airplanes, by the way. Before we ever fly an airplane, we model the heck out of it. And the potential for regional interventions. I mentioned tipping points. I'll show you in a minute what I mean. What I've been talking about so far is how do you adjust the planet writ large, not address specific tipping point events. And if there are tipping points that might be out there, does it imply we need an early warning system? And what would that constitute? I mean, how do you define a tipping point, and how do you define what the warning signs would be? But if you could, what would a monitoring system look like? Prudent risk management says you would take the outputs of all of those research efforts and you would assess the uncertainties and the risks. This is how we do the space program. We take all this input, we synthesize it, we analyze it, we make decisions on it. We don't just shoot from the hip. Based on that risk assessment, we might decide that subscale field tests are appropriate. With the right guidance and review, we would do it. And based on the feedback of those subscale tests, we may ultimately decide to try some form of geoengineering and monitor it. But this isn't being done yet. It needs to be done. I'm going to skip past this. This is some technical detail about how we might go about studying analogs. Just want to point out here, there have been some studies that suggest this idea of seeding clouds. Well, about 25% of the time, it actually makes the clouds darker. It makes things worse. So about the target interventions, I talked about how fast things are changing in the Arctic. Well, risk management would say, what are the threshold for some of these tipping points? Do we understand what would constitute, the equivalent of me falling off a stage? And what would be a warning? Is there like a little red line here that warns me that I've got a few steps before I hit this so that I can put the brakes on? Or I can get my safety net deployed. Maybe I don't leave it out there the whole time and it's expensive, but I can get the safety net ready before I get to the edge. And of course, if you're going to have early warning systems, the only way it helps is if either you can move people or prepare for the worst, or you can actually have credible interventions. And these are different interventions than what we talked about, right? I mean, my giant reindeer idea. Okay, so this gets to an issue about who needs to work on this. This is a transdisciplinary problem. We're talking about the coupled Earth system. Well, we're part of the Earth system. Economics, Social systems, politics, engineering, earth science are all part of this. And all of these actions, whether we're mitigating greenhouse gases, we're adapting to climate change, we're geoengineering, or we're not taking action, aka suffering, I'm going to make a prediction that some form of all of these things are going to happen sometime in the 21st century. And these decisions are connected. These aren't in a vacuum. I do something over here, I affect my ability to do something else. If nothing else, because I'm diverting funding. So again, this is a transdisciplinary problem. It's not just earth scientists, it's not just engineers. It needs to involve economists and the social sciences. And when you look at this and you're familiar with the way our society works, you realize this maybe implies a new way of thinking. Because we don't organize this way, right? We tend to be more stovepipe. So what would we do if we were thinking about the Earth as a system, where we're part of a system? If we think about the connections, sorry, I'm a system engineer, I think in terms of block diagram. The things that drive what we do to the planet are a function of population change, education, economy, available technology, carbon intensity, right? If I had better green energy technology, my carbon intensity would be lower. If I had certain economic incentives, it might, and if I had a grip on this, my demand for energy and other services would change. Those are the connections. Those drivers result in emissions and land cover change, which drives the chemistry and physics of the atmosphere, and ultimately the radiative forcing, the right-hand side of that equation I talked about. This leads to climate change and acidification, which has ecosystem impacts, the societal impacts that connect with each other. Now, if you're thinking about how do I get a grip on this, how do these impacts affect the left-hand side of the diagram? Well, in an ideal world, there would be a feedback, right? If things are getting bad over here, it's going to have an effect over here, over here, over here. But right now, because of the long time span that's required, we're talking decades, these are slow or open loop, as an engineer would say. In other words, they're not providing a feedback yet, right? So what we're doing as a society is we're doing open loop actions. We're going in and saying, I'm going to mitigate, I'm going to address carbon intensity and the economy and available technology to cut back on emissions, or to manipulate how I change the surface of the land. If we do geoengineering, we will be manipulating the chemistry and physics of the atmosphere, land cover, and some of the ideas actually address ocean acidification directly. This is the blunt hammer. And lastly, we'll respond by addressing this box, right? So when you think about it, if you're thinking about it from this perspective, it raises questions like, if I'm going to try to control this, how do I balance agility, or how fast I can respond to a changing environment with stability? The general tenet in control systems and engineering, you can change rapidly or you can change stably. It's hard to do both, and optimal control system optimization brings those two together, right? So I don't move too fast. What about equity? We're talking about people's lives and countries and economies here. So fairness has to fit into this. It has to be factored into the reality. And then what are the relative costs? What are the relative risk of doing this versus this versus this? And what do we need to measure, right? In the human system and in the earth, in the climate system. The last thing here is thinking about this from a timing perspective. I mentioned that it took about 150 years for us to carbonize the planet to the level we are now. In realistic, if you just think about the physical scale involved, it's going to take the rest of this century to decarbonize. That's the math, that's the numbers. So what does this mean in terms of putting all these options together? If we look, this is hypothetical, if we look out to say 50 years from now, mitigation and adaptation, this is plan B that we're doing now, are still ramping up. They need to be ramped up more. And you can imagine that once they get to some point, they should be sustained. This question of carbon dioxide removal, if we get to a point where we have to draw down CO2 in the atmosphere, it will take decades. So there has to be recognition that it's not going to happen overnight. It'll take decades. What about warning systems? Well, what would a warning system do? Let's just hypothetically say, if there were some kind of tipping point that we didn't want to go over, let's say it was out here 2035, and you could define a criteria that said, I'm coming up on it. What would my monitoring system have to do, and how much lead time would it need to give me? In this scenario, you might consider deploying solar radiation management right before this, right, to prevent the worst and to keep your umbrella up until this could take effect. But this implies research and risk assessment we haven't done yet, right? Because this is not safe to do yet. We're not ready to do this. I know this is hard for us to think about as a society because our political systems and our financial systems don't work on these kind of timescales. But this is the kind of thinking that's going to be needed because we have to think strategically. It's really important for younger people now because this is kind of the process we're talking about. It's not going to happen overnight. So with that, now what? Last slide. A colleague of mine at Colorado State University, Scott Denning, says this about climate change. I think he's right. In its fundamentals, climate change is simple, it's serious, and it's solvable. Despite all the graphs, despite the models and the data and everything, think about it. The basics are really simple. If you burn fossil fuels, you release CO2. CO2 traps heat. This has been known since the 19th century. If you trap heat, the Earth warms up. If the Earth warms up, things will change. You can argue about how fast they will change, when and where and how, but the things I showed you are simple physical processes. They've been around since the 19th century, or they've been understood since the 19th century. It's serious, I hope you see from what we've talked about, and it's eminently solvable. I hope that came across, that we're not talking about inventing unobtainium here. This is the scary thing, is the geoengineering could be done with quote-unquote existing technology. The complications are how we do the solving, and they're complicated by the fact that we've got rapid change and inertia in both climate systems and human systems. There are irreversible processes, and there are uncertainties in both climate processes and the decisions we'll make as a society. It's hard to project. Some of the largest uncertainties in what's going to happen the rest of a century are not in the climate models. They're in the societal projections. What decisions will we make? So we have to think about those uncertainties when deciding the optimal response. So geoengineering is definitely risky. It's problematic for the reasons we talked about, but rightly or wrongly, it's increasingly likely that someone, somewhere, somehow will try it. We're already starting to see the field experiments. So even if we never do it, we need to understand the risk. We need to start looking at geoengineering, again, in context with all the other options. And this probably requires a new way of thinking about the Earth system. It has to be end-to-end, like I showed, where part of the equation is the Earth climate system. And it has to be informed by research that's governed properly, and it has to be transparent. It has to be open to public scrutiny. Right? This can't be done behind a curtain. And it has to be transdisciplinary. This is beyond the domain of scientists and engineers. It has to include the social scientist and the economist and the public. Finally, Earth system stewardship. If this is an intellectual process, thinking, this is more of an emotional or a perception one, right? What we're talking about is managing the reality of a changing planet. It's changing. That's reality. So there's a different way of thinking about things here. It's a stewardship perception. So with that, I'll finish up and I'll take questions. So I've been asked for people who have questions if you could approach the mic because this is being taped. So if you could queue up at the mic so you'll be heard, and we'll just take first one.
I have two questions.
Mm-hmm.
The first is about the array of machines to suck the CO2 out of the atmosphere, and you said that was an inefficient process. So, and you said if you had 30,000 power plants, you needed half as many reverse power plants. So, but the reverse power plants are using energy. So how much energy do you have left after you run the reverse power plant?
That's right. Yeah, so I mean, there's not a good answer to this because it doesn't work out economically. The argument for how this would work is that you close the gap on the energy cost. It's the same argument that people are trying to do with solar, right? To make solar energy really take off, you have to close the gap per kilowatt hour from solar versus fossil fuels. The same thing applies here. The only way this will work is if you can close the gap, that is, make it more efficient, and it also assumes that you can raise the price of carbon. Right now, carbon's quote-unquote free. One of the things I didn't talk about is we don't do full cost accounting except in some places in Europe on carbon. So carbon is considered free. In many places it has almost no tax on it. So we have to do two things. We have to make the air capture more efficient, and we have to raise the price of carbon for it to become economically feasible. And right now, I personally don't see a plan to do that. I mean, I see plans, but I don't see us converging on it.
And the other question was about if you just take the most obvious feedback, the Arctic melting and the albedo change there.
Right.
I mean, how do you even assess where the tipping point is? It sounds like the tipping point's already been reached, right? I mean, what do you mean by assessing a tipping point?
So that's a really good question. So there are different tipping points within the Arctic. Let me go back to this figure real quick. The Arctic's a busy place, just like my slides. So there's a lot going on. You've got Arctic sea ice, right? And you've got permafrost. Where does permafrost shows up here in the Yodoma permafrost, over here in peat. Peat fires is also kind of part of this. Arctic sea ice is just one of the tipping points. So yeah, we may have passed a threshold for that. And, the assessment may be, well, okay, we're going to have an ice-free Arctic, and that poses geopolitical problems. The impacts on the rest of the world haven't been analyzed yet. So some of these other ones, though, we think are still far out in the future, for example, permafrost and some of the other ones. As for what you can do locally, they range from just focusing on changing the albedo, or the reflectivity of the Arctic. I was joking about the reindeer, but there are other ways to do this. The other one is the so-called Yarmulke solution. It involves doing the stratospheric aerosol injection just over the poles. So instead of doing the whole planet, the idea would be to put a cap of aerosols over the Arctic. The problem is the simulations show it quickly redistributes, and you have a global impact. That's one of the big questions here, is acting locally impacts globally in most of these schemes.
Thank you.
Yeah.
So I'm curious about the current thinking in the fossil fuel industry in this area. I'm starting to see geoengineering show up more in the literature, and my impression is that they're spending so much money on PR and everything else these days, and they're fighting climate change initiatives so intensively. You would think that this would be somebody's advantage in their thinking or whatever to promote this and to spend money on it. And so I was just kind of shocked when I read what I thought was a very thoughtful book, Watchman's Rattle, and this was promoted as a solution to climate change. All of a sudden, it came out of nowhere. So must be people out there pushing this. I just haven't seen it myself, but you must know more about whether the industry is putting money into this or whatever.
I haven't heard that. But you can imagine how there would be financial incentives for oil and gas production entities, because the air capture method has to store the CO2 somewhere. And so the irony here is that after we're done pumping all of the oil and gas out of the reservoirs under the earth, we'll turn around and stuff CO2 back in, which has got to be the scam of the century. You get paid both ways, because it's the same. The people have developed the same technology. That's how we're getting the last bit. It's similar to the fracking question. Right? We get the last bit of oil and gas out by injecting stuff. So I haven't heard that. What you do here in the air capture area is there have been challenges put down. Branson put down the Carbon Prize. This is the Carbon War Room entity he started. It's similar to the X Prize with the commercial spacecraft. And there's a prize for the first team that can sequester or capture 1 gigaton of carbon a year from the air and store it permanently. And so there are non-governmental entities and private entities who are trying to incentivize innovation along those lines.
Thank you. In regard to the plankton that's located off the northern coast of Chile, that's iron-fed, have there been any advances by the biogeochemistry faction that could possibly indicate that there might be other experiments in other places on the planet?
You mean, do we know whether people are conducting other secret experiments? That's a good question. It kind of gets back to my question about monitoring, because the early warning systems could do more than one thing, right? They could tell you about tipping points, but they could also tell you if somebody's doing the Dr. Evil thing off in the ocean. For the most part, this has happened a couple of times now, and when it happens, the companies that do it do a big press release, right? Or somebody gets wind of it. It's hard to tell, by the way, looking at a satellite image, because you get plankton blooms around the planet anyway because of natural processes, and doing attribution, what was caused by an intentional experiment versus natural, is hard to do. And our monitoring systems, or our satellite systems, aren't set up to do that. NASA's satellites are set up to understand the natural system and the whole planet and how things work together. They're not set up to find, illicit experiments. So the answer is we don't know. Somebody could be doing it. We don't know.
Additionally, is that the formation of diatoms that is essential in the creation of the planet, whereby the carbon dioxide in excess levels is possibly taken out of the air, as it were?
I didn't follow. Sorry.
Okay, diatoms is one of the methods that's utilized in regard to the plankton by the onset of iron being introduced into the area. And so therefore, is it primarily the basic method that's utilized in extracting the carbon dioxide?
That's one method. There are other methods that I would say they're like calcium reactors in your fish tank. Have you ever seen a marine fish tank? Where instead of actually trying to stimulate plankton blooms like diatoms, you might inject calcium carbonate into the ocean and through a chemistry actually induce or actually sequester carbon in more solid form. There are a number of ocean schemes. I only showed you one, right? And I showed you that one because people are actually doing it right now. The other ones are all, as far as I know, on the drawing board.
Doesn't the type of method that's utilized depend upon the elevation of the ocean involved?
The elevation of the ocean. It depends more on the current state of the ocean, I would say, which includes the current pH state and the biogeochemistry. So what we might try in one part of the ocean today and what somebody might try in the future might be different. But again, these are all interesting research questions. This is not mainstream research. It is an open-ended experiment. People are playing chemistry experiments with the ocean without necessarily being able to predict the outcome very well.
Thank you.
I think you made a very good case in your talk for not doing geoengineering, and that makes complete sense. In fact, something that you said, aside from planting. So plants are the answer. In fact, that's how nature has maintained its balance for billions of years. And now that we came along, we are doing good things. Civilization and technology is helping us get better. But if we keep in mind about planting, for every little plant we build, if we, that is the answer, really.
Yeah.
Because plants have a lot of power in sucking back that carbon dioxide. So in proportion to that, if we can do that, and if we study that thing, in fact, personally, I've been studying that issue. What's your thought about that?
So it's true. I mean, obviously, we would like a natural solution. The problem is the fossil fuel use is drastically outpacing the natural system's ability to keep up. And so you would have to somehow accelerate the biosphere to keep up with it. So accelerating the biosphere on land is equivalent to accelerating the biosphere in the ocean with the fertilization. And there are people who've looked at that. Again, it's a question of scale. How do you scale up the ecosystem to do that at the same time that we're doing deforestation? So yes, in theory, but offsetting the current acceleration in fossil fuel use is a hard climb. But I agree with you. Your main point is the one I was trying to make, is that if you look critically at this and you look at the relative cost, right, the answer has to be that mitigation is cheaper and safer, and in the long run, it's the solution. The question is, will we decide to do that in time?
Each of us at our personal level can decide to do it, and it will happen. Because the unit power then extends, and if each child, teaching more about how plants grow and how we can make them happen.
And also making people aware of what our fossil fuel footprint is, because if we don't stabilize that, we won't keep up with it.
Reducing the use, sustaining, conserving, basically.
Right. Thank you.
Yeah.
I have two questions. One was, I noticed along with fossil fuel on the y-axis, it talked about cement production. How does cement production produce carbon dioxide?
Oh, great question. So cement is made out of limestone, which includes calcium carbonate, which has been stored there. And actually, one of the geoengineering methods I didn't talk about is called weathering, enhanced weathering, where we actually try to put more of the air, the atmospheric CO2, into a solid form. So just like with fossil fuels production, when you burn coal and you release the carbon that was stored, if we take limestone and we grind it up and make cement, we release the carbon that was stored in the limestone. Limestone is what is the long-term storage of this stuff. That's what ends up in sediment at the bottom of the ocean.
Then the other question is, I know there are bacteria that can convert methane to carbon dioxide. Is anyone investigating using maybe genetically engineering bacteria in the permafrost to convert some of the methane to carbon dioxide?
Yeah, so I mean, the point I made about we don't know what fraction of the permafrost will come out in CO2 versus methane definitely depends on the conditions of the methanogens that are there. That's the whole point. If there's a different fraction of wetness and oxygen, you'll get the methane critters versus CO2. And I'm sure someone's thought about that. It hasn't been talked about as a major option. In fact, methane capture hasn't been talked about that much yet. We're still trying to get our arms around how much is there. Yeah.
Thank you.
Just have a quick statement and then a question for you. If you've noticed, there's a lot of companies that are talking about going green. For example, British Petroleum no longer calls itself a petroleum company. They call themselves an energy company. And about a third of what they own energy-wise is solar, windmills, and that sort of thing. And of course, they're getting a lot of feedback and complaints from people about, don't build that windmill in my backyard. So there's, you try and do good, you get bad. My question for you is, injecting water at high altitude, is that a plus or a minus, and how long does it last?
Right. These are really good questions. That's actually one of the big research questions. One of the things we don't know about the stratospheric aerosol injection is what does that do to water in the atmosphere? In other words, there are pathways between the upper atmosphere, the stratosphere, and the lower atmosphere, the troposphere. And we don't understand the mechanisms of exchange. And so one of the concerns is that doing this will actually increase more water vapor in the upper atmosphere, and that could actually end up trapping more heat. So this is, in other words, it may work over short time scales with some of the volcanoes, but we don't know the answer to that question. Water, also what happens to the ozone layer. There are chemical processes that result from mucking around in the atmosphere. We could actually accelerate degradation of the ozone layer, which is something we're finally getting our arms around after several decades with the Montreal Protocol. And there are questions about what happens when these sulfates rain out into the lower stratosphere. What are the impacts on cirrus clouds? So yeah, water vapor is a big question. We don't know. Injecting water into the stratosphere would be probably counterproductive because you'd end up trapping water. Water is a very potent greenhouse gas, so we don't want more water.
Okay.
I barely heard you mention overpopulation in your talk. China is the only country I know of that has some attempts at overpopulation. One needs only to go to the zoo. Almost every large animal is endangered now by human intervention there. What can be done about human population?
Bingo. So thank you for pointing out this block. This is simple arithmetic. The amount of energy that we collectively demand and other demands like land and clearing land and having places to live is driven by two numbers. It's the population and then the carbon intensity, right? And this figure here kind of shows it. I didn't have time to go over this. This is a plot of wealth expressed as gross domestic product per capita or per person on this axis over some years. And this is a plot of carbon intensity, or how much CO2 we emit per person based on what we demand. And what you should take away from this is two things. One is, in the developed world like the US and Europe, more wealth equates to a higher carbon intensity because we have more, the products we demand, the energy use is much higher. And the other thing is that, you know, these other countries are developing, so they're moving up. And this comes back to that inertia comment I made earlier. So it's the combination of the per person carbon intensity based on the demand we have and the number of people that's making this hockey stick curve with the CO2 accelerating. Until this settles out and until the population settles out, we're going to keep seeing that kind of growth curve. And you know, the UN predicts that we're going to see urbanization double by 2050. I mean, the number of people who live in cities. And cities, it's an interesting thing here. Cities, in many cases, are better for us because our per capita energy use in cities tends to be much lower than it is in rural areas because you concentrate resources. So there are several effects happening, right? You've got countries that are growing very rapidly, both in terms of population and economy, and then you've got the fact that most of them are moving into cities, which means their carbon intensity will drop. And where these cross is a great, you know, social science question. And the other reason why I showed on this block diagram the connection between population rate and education is that it's been shown that, you know, the biggest impact on population growth rates is education, particularly education of women. So that's, you know, some of the knobs we have to turn, let's not forget, are not over here in the physics world. They're over here in, you know, get back to basics, education world and economic world.
I want to go back to the first picture you showed about the Nile, the River Nile, and the Mediterranean. The question was about the fresh water. As a matter of fact, you know, that the original thing was about, since the time of the pharaohs, the amount of the water practically has not changed in the River Nile. But lately, there was mention about, both in the Nile and the Euphrates, about the decline in the amount of fresh water. And that's probably because of the increase of the carbon dioxide, whatever the many reasons there. And they are not the ones who are causing it. I mean, as you showed in the pictures about in China and Europe, with the increasing, I mean, the Egyptian or the Iraqis or anybody, they are not the one who is causing that thing.
That's right.
I was born and grew up around the Nile, and I'm very familiar with what is going on. One of the things is that, yes, they have a lot of problems with the fresh water. And, I mean, now, problems created by some people is affecting other people, okay? And of course, I want to get also to the point about the Kyoto Agreement. You did not mention anything about that with the carbon and and the American refusal to sign it. I mean, I don't know if you can shed some light on that.
Yeah, so the water thing's really interesting. Most of my effort, by the way, is not geoengineering. Most of my effort is on mitigation or reducing greenhouse gases and how do we support the international agreements on stabilizing it. And it's also an adaptation, in other words, what's happening with water. And so we work with agencies and people in this part of the world who are worried about the water supply. And so there are two things happening, right? There's consumptive use because of the population growth and the development. And we can actually see water being drawn down. You know, scientists look at groundwater and they see the aquifers being drawn down by consumptive use, just like we are in the U.S. And then we worry about supply changing because if precipitation changes, then either directly the precipitation impacts or rain impacts on rivers, or in places like the Hindu Kush and the Tibetan Plateau, where most of the rivers in Asia are fed by glacier melt. And we're seeing, we can see from satellites that the glaciers are melting. The peak runoff period is the time of it and the magnitude is changing because of dust. Dust settles on the snow, and there are people here at JPL who are experts in looking at this. So it's a combination of factors. It's the climate-induced factors that affect the supply that are caused by people far removed from this, and then it's the local impacts of consumptive use. And this is recognized as a big issue in the climate negotiations. It's called the social cost of carbon. In other words, a remote impact causes the local problem. And with regards to the Kyoto Protocol, the UN Framework Convention on Climate Change continues to have annual meetings every year where they're trying to come up with an agreement or follow-on to Kyoto. And the best that they've been able to do is to agree that they're going to come up with a plan by 2015, and that it will go into effect in 2020. Now, in the meantime, let me give you some optimism that we have. In the meantime, some countries aren't waiting. Do you know the two countries that reduced their emissions over the last few years? The U.S. and Germany. Not necessarily because we were implementing the Kyoto Protocol, but because in the U.S. case we're transitioning more to natural gas. It has its own issues, but in terms of CO2 it's reduced. The other thing to notice, and I know this because I work with the cities, we have a mega cities carbon project where we're focusing on the world's largest cities. The cities' mayors aren't waiting on countries. They are implementing policies now. Mayor Villaraigosa, Mayor Bloomberg, the mayor of Paris, the mayor of London, the mayor of Sao Paulo, Beijing. They have their own network and they're doing their own thing. They're not waiting for a Kyoto agreement. And that gives us a lot of hope because cities and the power plants that drive them are responsible for 70% of fossil fuel emissions. So action is happening. People are paying attention. You're seeing a lot of leadership at lower levels of government that don't get a lot of press. So that gives me some hope.
With all this Arctic ice that's melting, when is Florida going to be sunk?
So the sea ice melt really doesn't contribute to that because the ice is already in the water, and so it doesn't contribute to the melt. But the concern about sea level rise has more to do with ice sheets. I didn't talk about that, but what happens to Greenland ice sheet, the glaciers there, and Antarctica in particular, is a big concern. And they are melting. We're seeing melting, but the consensus is that's happening slower than the sea ice. So the sea ice looks really scary, but the big impact from that won't necessarily be sea level rise. It's the ice sheets in Greenland, and they appear to be taking longer. But again, there are large uncertainties about when will they hit a tipping point, and that's active research. In fact, a lot of people here at JPL are some of the world's experts in studying physical oceanography and the sea level problem, and they're experts on the ice sheets, and that's we have a lot of work in that area to go.
Well, didn't we have at one time in our history that Greenland was pretty much ice-free?
At some point in Earth's history, that was true.
Well, with
when we say our history.
Well, I mean with the Vikings.
Not ice-free.
There were people that were able to live there, and
but it wasn't ice-free.
No.
You have to literally. I mean, if you take the long view, you can go back in time and find an Earth that was, all green, but it was millions of years before our species ever arose, and long before we had agriculture. Agriculture is only a few thousand years old, and there's a reason for that. Probably it has to do with stability of the climate system.
Well, I get the impression that what we're doing, all of this is caused by us, and we're slowly suffocating ourselves in the future.
Yeah, I don't know if it's suffocating, but we're certainly making it hard on ourselves. Yeah. Hopefully we'll learn fast. Yeah.
Thank you.
Mm-hmm.
As they predict in 2013 to be the maximum solar activity, solar flares. I don't know if you guys subscribe to the Science News. They just had a news bulletin yesterday in the UN that they are talking seriously about solar activity affecting climate. Is there can that happen? Can solar flare have a negative or a positive effect on the climate?
Not in the long term. One thing to remember is that climate is not, it's important not to think about climate like weather or to think about it on short time scales. I didn't show you Let me just show you this maybe to make the point. I didn't get to this slide, but the Earth, when we talk about climate, we're talking about long-term changes, right? They, you know, the kind of the running joke with climate scientists, if you don't like the weather, wait 5 minutes. If you don't like climate, move. Let me try to explain that real quickly, and then I'll come back to the solar stuff. So these are two plots taken from NASA satellite data and historical records. The top one's showing CO2 in the atmosphere. That's our AIRS instrument that we built at JPL. And the bottom one, these are very different time scales. The top one is just going from 2002 to 2008. And the bottom one is showing temperature going all the way back from 1880. And what I'm trying to convey in these plots, and they're going to loop here in a minute, is look at what's happening in the temperature plot and even look at what's happening in the CO2 plot. You've got changes happening all over the place, and it's oscillating back and forth, right? And things aren't changing at the same time. But if you watch over the long term, what you'll notice is this plot's going to go from mostly blue to mostly yellow or red, because the trend over decades is getting in one direction. And the same thing with CO2. Even though you're getting these seasonal variations and these patterns, over a long time, that plot went from blue. So that's when we talk about climate change, you have to think about long time scales. And the sun does fluctuate, and there are impacts to the Earth system when we get solar flares, but those are quick, and that's natural variability. What we're talking about with climate change are long-term synoptic changes that drive us away from, you know, the conditions we know now on average. That's why we'll say that it's not that we're suddenly going to get 100 hurricanes every year. It means the general amount of extreme events goes up, and that trend continues.
Thank you.
Okay, so we're at 8:30, so I think we're at the end of our broadcast, so thanks for coming out, and go enjoy Valentine's Day.